Okay, so today we are going to talk about the singular value decomposition, or just called the SVD algorithm. Actually, this is the last lecture in this semester. Actually, it's not a last lecture, but because we have a homework 3 review in third day, but this is the last lecture for the our textbook. Okay, so let's start. So before starting, there is a notification for the homework 3. So due date of the homework of this homework due on June 17, Wednesday until midnight, right? So and there are several problem set from our textbook. So please check this problem set, and as usual, you have to submit the photographed or the scanned file electrically in Blackboard. Okay. So this is a homework 3. And as you know, in this semester there are so many unexpected things. So we have to change our final grading policy. So this is our final grading policy. So first of all, actually in this semester we had 3 homework assignment, right? So for each homework will have the 10% 10 percentage of your grade, and we will have a final exam next week, but we are not deciding the online exam or the offline exam yet, because there are so many arguments. So I will let you know as soon as possible, but we will have a final exam. So the credit of the final exam will be the 65 point or 65%, right? And one more thing is that class participation. This is subjective things. Okay. Anyway, this is our final grading policy. Okay. So let's start today's lecture. Before starting, I have something to let you know. There was some typo error in our previous slide. So okay, so if you see the lecture 8.1, this is lecture 8.1 in page 9. There was the typo error here. In this case, this should be I, right? Because this term defined on the I comma j entry, right? So ci comma j is equal to -1 superscript I plus j times the determinant aij, right? So I have to fix this one. And another thing is that in lecture 13.1, in here, there was a set of the vector v1 through the vr, but in this case, v1 is here, vp is here, right? So in this case, this set should be defined from the v1 through the v1 to the vp, right? So please, yeah, please check this one again. Okay, so yeah. So okay, so let's go back to today's lecture. Okay, so today we will talk about the singular value decomposition. Actually, this is the last matrix decomposition method. In this semester, in this course, we will talk about many matrix decomposition techniques. First of all, LU decomposition, QR decomposition, or the eigen decomposition, or the spectral decomposition. And as I mentioned previous lecture, the eigenvalue decomposition is very powerful things, can be used in many applications, but it is limited on the symmetric matrix with the n by n matrix. So it has very this constraint is very hard to limit. This constraint is very hard to apply. So we need a more generalized version of the decomposition. So this is the singular value decomposition. So the diagonalization plays a part of in many applications, as I mentioned here and mentioned previously, right? So something kind of the eigenvalue decomposition or eigendecomposition, right? Eigendecomposition. Unfortunately, not all the matrix can be factored as the A is equal to P the P inverse, right? So in this case, P is just diagonal, right? So we can now apply the eigenvalue decomposition to the n by n case when n is not equal to n. But however, the factorization A is equal to Q the P inverse is possible for any n by n matrix, right? This is actually special case of the diagonalization. So we call this factorization as a singular value decomposition. Okay, so today we will talk about how to estimate the Q, T, and P inverse, right? For given arbitrary matrix A with the n by n matrix. Okay. So this is the today's goal. So let me start. Actually, I think that this today's lecture is one of the most difficult lecture in this semester because this is the last lecture. So to understand this lecture, you have to know the several kinds of the definition or the concept that we discuss in this semester, something like a length or the dimension or the basis or the eigenvector, eigenvalue, something like this. So before taking this course, please go back to our previous lecture and try to understand those kinds of the previous things as much as possible, and then start to study this chapter, right? So in this chapter, I will just assume that you already know the our previous concepts, and then I will just briefly mention to you about those kinds of concepts. Okay, so let's start. Okay, so first of all, matrix A be a n by n matrix, then we can easily find out that A transpose A is a symmetric matrix. A transpose A is a symmetric matrix, right? So, okay, let me write this. A transpose, the size of A transpose is n by m, and size of the matrix A is n by n, right? So the size of the A transpose times A is the n by n, right? And this matrix is also symmetry. So we already know if the matrix is a symmetry, then it can be orthogonally diagonalized, right? So you know the meaning of the orthogonally diagonalizable, right? So it was the previous lecture 40.1, right? And let's say the V1 through the Vn with the also normal basis for the Rn space consisting of the A transpose A. In other words, this V1 through the Vn be the also normal basis of the matrix A transpose A, and then let's say the lambda 1 through the lambda n be the associated eigenvalues of the A transpose A, right? Then the following equivalent can be found. The square of the length AVI is equal to AVI transpose times AVI, right? It's just like definition of the length, right? And then by using the properties of the transpose, matrix transpose, we can rewrite that vi transpose times a transpose times a times vi, right? And we already know a transpose a v is equal to lambda v, right? Because this is the eigenvector and this is eigenvalues of matrix A transpose A, right? And we can find out that this term will be something like this, with the vi transpose here, right? And what else? Lambda I is, because the lambda I is just the constant term, and vi transpose vi is equal to 1, right? Because this is also normal basis, so we can say that this is just lambda I, right? This is just lambda I. So in this case, the singular value A means the square root of the eigenvalues of the A transpose A denoted by sigma 1 through the sigma n, when sigma I is the square root of the eigenvalues, right? So this is just the definition. So we define the singular value of the matrix A as a square root of the eigenvalues of the A transpose A denoted by sigma 1 through the sigma n, and as you can see here, the sigma square root of the sigma I is just the length of the AVI, right? From here, right? So in other words, the singular values are the length of the vector AV1 through the AVN. Okay, so from here, so this is the definition of the singular value. So today, by using this definition of the singular value, let's derive the singular value decomposition theorem. Okay, so before that, there is one more theorem. Suppose the V1 through the Vn is also normal basis of the Rn space, consisting of the eigenvectors of the A transpose A, right? Defined something like this, and arranged so that the corresponding eigenvectors of the A transpose A satisfy here, right? So this eigenvector corresponding to this eigenvector corresponding to this eigenvalues, but those eigenvalues has inequality, something like this, which arranged so that the corresponding eigenvalues satisfy this one, right? And suppose A has R non-zero singular values. A has this is the definition of the singular value. So A has a R non-zero singular value. Then A times V1 through the A times VR is the orthogonal basis for the column space of A, and length A is equal to R. So this is just one theorem. So in other words, if we can find out eigenvectors and eigenvalues of the A transpose A, and we already know the A has R non-zero singular value, then AVI through the AVR is orthogonal basis for the column space A, and length of the A is just R. Okay, so first of all, let's prove this theorem first. So yeah, so actually the proof of this one might be very difficult, but just follow the sentence by sentence. So first of all, because the vi and the lambda j vj are orthogonal for I is not equal to j, right? Why? Because vi time vi is just equal, right? Because by definition, right? And then a vi transpose times a vj is equal to vi transpose times ai transpose times a times vj, right? Then vi transpose times here, this is just defined like this, right? This is definition of the vi and lambda j, and this term is something like this, and from here this is just 0, right? In other words, each vi and vj's are orthogonal each other, so av1 to the avn is an orthogonal set. Okay, so first of all, we know if the v1 through the vn is defined from the a transpose a, then av1 to the avr are orthogonal set because they are orthogonal each other. And since the length of the vector v1, av1 and avn are singular values of the a, right? So from definition, the length of the vectors are singular values of the matrix A, right? And there are r non-zero singular values. So we can say that AVI is not equal to 0. AVI is not equal to 0 because there are only r non-zero singular value, right? So if I is not equal, I is smaller than the r, then we can say that AVI is not equal to 0, right? Because there's r non-zero singular value and the length of the vectors are singular values, right? So from here, AV1 through the AVR linearly independent vector, right? Because they are not equal to 0 and they are orthogonal set, right? So AV1 through the AVR is linearly independent vector, and they are in the column space A, right? So the column space A means the linear combination of the columns in the vector A. It means that it can be the column space of the matrix A can be defined something like this, right? So in this case, X is replaced by the VI. In this case, A is replaced by the VR, right? So each vectors in column space, right? And then any arbitrary vector y in the column space A, something like this, define something like this, y is equal to ax, and we can write the x is equal to linear combination of the v1 through the vn, right? Because because the v1 through the vn is also normal basis, so any vector x, arbitrary vector x, can be defined by the linear combination of the v1 through the vn, and then y is equal to ax can be reformulated as c1 times a times v1 plus cr times a times vr plus blah 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 cn a vn, right? And then what else? Actually, we already know distance AV1, AVR is not equal to 0 because this one, there's a R non-zero singular value, but after that, this is just the non-zero value. So this is the zero value. So this term will be zero here. So finally, why can we rewritten by C1 AV1 plus blah 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 C1 AVR plus 0 0 0 0. Okay. So from here, the vector y can be represented by the AV1 through the AVR, right? So in other words, we can say that matrix vector y is in span by the AV1 through the AVR, which shows that AV1 through the AVR is an orthogonal basis for the column space A, right? Because any arbitrary vector y in column space can be represented by the linear combination of the AV1 and AVR, right? So or spanned by AV1 through the AVR. So we can say that these vectors are orthogonal basis for the column space A. Then what is the rank of the matrix A? The rank of the matrix A is the dimension of the column space A, right? If you remember the dimensional rank chapter, maybe it was what was that? 7.2. Okay, anyway, please check the rank chapter. Then the rank A is equal to dimension of the column space of the matrix A, right? Then what is the dimension of the column space of the matrix A? Because the dimension is just the number of the bases in basis for the column space A. So in this case, this set is the basis. This is the basis. So dimension of this basis is what? R, right? The number of the vectors in the basis, right? So in other words, the rank A is just R. Okay. So that's it. So in other words, if we have the eigenvector of the A transpose A and eigenvalue A transpose A. Okay, so if we define the eigenvectors as a V1 through the Vn, then AV1 through the AVR is the orthogonal basis for the column space, and rank of the A is just R. Okay, so in this time you might not understand this meaning, but by using this theorem, we will derive the singular value decomposition technique, singular value decomposition algorithm. Okay, so let's do that. So if we go back to our first page, we want to represent the arbitrary matrix A as a QD P inverse, right? QD P inverse. By the way, D is the diagonal matrix in eigenvalue decomposition, but in the singular value decomposition, the T will be transformed to the sigma, another n by n diagonal matrix sigma of the form D 0 0 0 0. So let's say that if the matrix A is n by n, then we can find out the m by n diagonal matrix sigma defined something like this. So the size of this matrix should be m by n when there is the m minus r rows because this is matrix D. Size of the matrix D is the R by R, and there is the N by R column. N by R columns. Okay, so similar to the diagonalization, matrix diagonalization, we transformed this matrix A to this sigma matrix by using the some matrix defined U and V, which we'll discuss later in this chapter, but we will generate this diagonal matrix where matrix D is the R by R diagonal matrix for some R not exceeding the smaller of the n by n. It means that R should be smaller than the n, m or n. Okay. Anyway, it is the R by R diagonal matrix. So, in other words, by using the singular value decomposition, we want to make okay. Let's say there is a matrix, some arbitrary matrix here and here, but in this diagonal matrix, the shape of the diagonal matrix is something like blah blah diagonal matrix define D as a 0 0 0, right? So in the later we will talk about how to find out this one. Actually, it is defined U, and how to find out this one. This is defined VT, and how to find out this matrix D. And then we can decompose the arbitrary matrix A, whose size is the m by n. Then we can decompose this arbitrary A as a U sigma V transpose. In other words, U sigma V transpose. Okay, so let's do that. Okay, so this is the singular value decomposition theorem. Actually, this is the last theorem in this semester. It means that it's one of the most important theorem in this semester. So please remember what is the singular value decomposition and how can we do that, and what's the meaning of each vectors and each matrix in the singular value decomposition. So let's start. Okay, so let's say let matrix A be a m by m matrix with rank R. So it's not a scalar matrix anymore. This is the m by m arbitrary matrix. Then there exists a m by m matrix sigma similar to here, for which the diagonal entries in D are the first R singular values of the A. So what was the singular value? Eigenvalues, scalar root of the eigenvalues of the A transpose A, right? Anyway, so the first R singular values of the matrix A define sigma 1, sigma 2, blah blah, sigma R larger than 0. Then there exists m by n orthogonal matrix U. So do you know the orthogonal matrix, right? So we discussed this one in the last week, right? What was that? If the orthogonal matrix, if the matrix U is orthogonal matrix, the matrix U satisfy this one, right? It means that each columns of the matrix U are orthogonal each other. Orthogonal each other. So let's go back. Okay, so this is here. So such a matrix has an orthonormal column. So vector U1 and U2 or the U3 orthonormal each other. So this is the definition. Anyway, there is a m by n orthogonal matrix U and m by n orthogonal matrix V defined such that. So any arbitrary matrix A can be decomposed as a U sigma V transpose. Okay, so this is the singular value decomposition. I think this decomposition technique is the most popularly used in many applied linear algebra fields. So please remember this singular value decomposition technique. So first of all, so this theorem say that there exists this matrix, this decomposition with the matrix U sigma V transpose. Okay, so let's think about how to find out this matrix U sigma V transpose. So before starting, any factorization, A is equal to U sigma V transpose with the U with our orthogonal matrix. Sigma is in the 3. Actually, this is 3. 3. And positive diagonal entries in D, positive diagonal entries with R singular values, right? Then this decomposition is called the singular value decomposition, or SVD of the matrix A. SVD of matrix A, and the columns of the matrix U in such a decomposition are called the left singular vector of the matrix A, and the columns of the matrix D are called the right singular value of the matrix A. Okay, so in other words, okay, so there is a matrix A whose size is m by n, and first of all there is a matrix U whose size is m by m, and there is a sigma matrix size is m by n, and V transpose size is n by n. Okay, so in this case the columns of the U called the left singular vectors of matrix A. So columns of the matrix U, this one is called the left singular values, or left singular vectors of A. Columns of the matrix V, columns of matrix V. So in this case it should be something like this. Why? Because there is a transpose here, right? So this one is called the right singular values of the matrix A. Okay. So right singular vectors of matrix A, right? And yeah, and so yeah, this is the definition of the singular value decomposition. So okay, so let's prove this existence. So first of all, let's lambda I and vi be asked in the above theorem. So if you remember the previous theorem, so here lambda I and vi defined as eigenvalues and eigenvectors of the A transpose A. So let's say if the vi is the eigenvectors of A transpose A, lambda I means eigenvalues of the A transpose A, right? Then we already know the AVI AV1 through the AVR orthogonal basis for the column space A from this theorem, right? Orthogonal basis for the column space A, right? Then to find out the orthonormal basis, we have to normalize each vector vi, AVI to obtain the orthonormal basis U1 through the UR. So we can easily do that. UI is equal to 1 over length AVI, 1 over length AVI times AVI to make a size of this matrix vector U as 1, right? So this is just a normalization. And we already know sigma I is the length of the AVI, right? So in other words, 1 over sigma I is equal to A times VI, right? And then from this term and this term, AVI is equal to sigma I UI. So when I is smaller than R, so please check that if matrix A times X is equal to lambda X, it was eigenvectors, right? But in singular value decomposition, there's a new term, AVI is equal to sigma UI. So compare this one, right? Anyway, so from here, so first of all, we know the U1 and UR, right? But the final matrix U and final matrix V should be m by n, m by m, and m by n, right? So this one, actually this, if we matrix U with the U1 through the R, the size of the matrix will be the just m by r, right? So first of all, we have to extend U1 through the UR to the orthonormal basis U1 through the UM of the RM space. So it means that this is non-unique. There are so many methods. There are so many possibility of different V, different U. Okay, so we can extend this U1 through the UR to the orthonormal basis U1 through the UM by using any kind of technique, So it means that it's not a unique matrix. Anyway, let's say if we expand this matrix, this set of the vectors to the orthonormal basis, then by construction, matrix U and matrix V are orthogonal matrices. Matrix U and matrix V are also orthogonal matrices, right? Then where is that? So okay, so let's say this is the equation 4. So from equation 4, AV, because this is A times the vector V or I, but matrix A times matrix V is equal to AVI is equal to something like this, right? So this one is equal to sigma 1 U1, AVR is equal to sigma VR, and then just 0 here, right? And let's say the matrix D be the diagonal matrix with the diagonal entry sigma 1 through the sigma r, and sigma is defined above, similar to the here, right? And then u times sigma, matrix u times sigma is equal to u1, u2, um with this sigma matrix, with here is the matrix T, and here is the 0 here, right? This is a u times sigma, and if we compute matrix computation between these two matrices, then we can compute the sigma 1 u1, sigma 2 u2 here, and sigma r ur, because there are ur somewhere, right? And the remaining things are 0, right? So this is a u times sigma. So if you remember this term, AV was equal to sigma 1 u1 through the sigma r ur and 0. So this term, this matrix are exactly same to this one. So we can say that u sigma is equal to AV. Sigma is equal to AV, right? So if I rewrite this one again, sigma is equal to AV. And then matrix V is equal to orthogonal matrix. And orthogonal matrix means U inverse, V inverse is equal to V transpose, right? So if we compute sigma V inverse is equal to just VA, right? So in other, this is U sigma V transpose from here, right? So that's it. So from here, so here U sigma V transpose equal to UA V transpose and equal to A. Okay. So in other words, the matrix A can be decomposed as a U sigma V transpose, and this actually, as I mentioned here, this decomposition is not unique. There are many possibilities. Depending on how can we expand this u1 to the ur to the orthogonal basis, then there are so many possibilities, right? Anyway, so this proof shows that there exists the u sigma V transpose or V that can be the decomposed matrix from the arbitrary matrix A, right? So this is called the singular value decomposition. So it's very easy. So by using this singular value decomposition, let's decompose the arbitrary matrix A by using the singular value decomposition.